Aloha nui kako. Welcome to another edition of Live from NOIRLab at Hawai'i. My name is Alyssa Leinani Lozi, and I will be your host for today. Joining us is Jamika Marshall, who will be our moderator, taking all of your questions in our YouTube chat. And our special guest is Vinicius Placco. Vinny is an associate scientist at NOIRLab and CSDC, working in the U.S. National Gemini Office since September 2020. He obtained his PhD in astronomy at the University of Sao Paulo in Brazil. He held postdoctoral positions in Brazil at NOIR in Tucson and as a Gemini Science Fellow in Hawaii. Between 2015 and 2020, he was a research assistant professor of physics at the University of Notre Dame. His research is in the field of stellar archaeology, focusing on the origins and evolution of the chemical elements in the Milky Way galaxy and the universe. Hey, Vinny, thanks for joining us today.
Hello, thank you for having me.
Okay, now before we let Vinny tell us about his amazing science, we're going to talk a little bit about Gemini Observatory, which of course consists of two twin telescopes, one located here in Hawaii near the summit of Mauna Kea, and the other located on Cerro Pachón in Chile. Gemini is an internationally funded organization with participants from the United States, Canada, Chile, Brazil, Argentina, and Korea. And for our Gemini science highlight, we have a recent press release available on the NOIRLab website at the link below. And this press release is about CK Velpeculae, which is a sort of star, a very bright object that was thought to be the first nova discovered in 1670. But some recent observations have found that this object, this exploded star, is much further than expected. So it's now thought to be a somewhat odd classification of nova, bigger than a nova, but smaller than a supernova. And so it's a pretty exciting new object that astronomers are trying to piece together. So if you want to learn more about that, you can once again check out that link that is here on this slide. Okay, and with that, we'll let Vinny take it away.
Okay, thank you very much, Alisa, Jamika. Let me share my screen with you. So please let me know if you can see my slides and hear me well.
Looks great.
Okay, thank you. And I should have my pointer here. Let's see. Yes, I do. Okay. So, well, thank you very much for this very nice invitation to present a little bit of my research to everybody who's watching. Thank you all for taking the time to see this presentation, and I'm really happy to be here. I've been one way or another connected to the Gemini Observatory for over 10 years now. When I first started observing when I was still a graduate student back in Brazil. And I have to say that it's really rewarding for me to be able to stand here today as working as a scientist for this great institution and be able to present some of my science to you. I think there's a big thanks for many people who supported me over the years, my family, my wife was here with me, and everybody who's believed in me, and now this can be a reality. All right, so the theme for today is the age and the chemical evolution of the universe from two stars in the Milky Way. Let's see. The first thing I would like to say is that, well, I really like this cartoon here from Calvin, and you can see on the bottom here, Calvin is just staring at the night sky, and then he just screams, "I'm significant." There's no answer to that, and then he says, "Well, scream to the dust speck." I think in a way, what Calvin's trying to tell us is that when we compare ourselves with the vastness of the universe, I think we can really realize how small we are. Not that we are not important, but we are really small in the scales of the universe. And that goes also along the lines of what Carl Sagan would tell us, who is one of maybe the greatest science communicators of all times in astronomy, He passed away many years ago, but he says, if you want to make an apple pie from scratch, you must first create the universe. So what he's trying to tell us is that if we want to understand everything we have here on Earth today and the sun and in the Milky Way, we first need to understand how the universe came to be and how everything that is in the universe today, how all of those things were formed. Okay, so bear with me and hopefully this will be a really good presentation. But first, what I'm trying to tell you is that I want to tell a story about the age and the chemistry of the entire universe by just looking at 2 stars. So before I go into the astrophysics of it, let's talk a little bit about numbers. So first, I have a small question for you, and you can answer that on YouTube if you want, or you can just do that as a thinking experiment, and I'll just give you 10, 15 seconds to answer. So how many emails do you think were sent in the year 2019? So here's a figure about what happens in the internet in 60 seconds, just so you have an idea of the numbers. So according to this study, in 60 seconds, 190 million emails are sent. So how many emails do you think were sent on the entire year of 2019? You can write an answer on YouTube, and I'll just give you a couple of seconds to think about if this number is too large, too small, but just so we have an idea of how all of those numbers compare with other things we can see in the universe. I'll give you the answer so you can compare with what you thought. So I see Jamika here, yeah?
Hello, Vinny. All right. So in the YouTube chat, we have an answer from Joel Riverboat. He says 10 million, possibly.
Okay, 10 million. Okay, I think it's more than that in 1 year, right? Because here it says 190 million in 1 minute. So it's a good guess, but I think it's more than that. Do you have any other?
Oh, wait. So he says, Joel says, oops, 10 billion.
Okay, 10 billion.
10 billion.
Good. So let's use that as a template. So the answer I have is this one. So we have this big number of email. I think it's 70 trillion emails in 1 year, which is roughly 10,000 emails for each living person on the entire planet. So you may think that this number is large, small, but let's take this, just stay with that number in your head. So how do you think that number actually compares with the number of stars that we see that we know are in the entire universe? So I'll give you another 10 seconds, just 1 or 2 guesses. So do you think that the number of stars on the entire universe, it's much smaller, much larger, about the same as the number of emails we just talked about? Just take a wild guess, and then we'll move forward. You can try to think in terms of scientific notation, billions, trillions, quadrillions. That's not very important, but just think about it. In your own head, do you think that those numbers should be comparable, much larger, much smaller? I'll give you another 5 seconds. Let's see, I'm just looking here at my watch. I'll just drink a little bit of water. Do you have something, Jamika? Yeah.
So yes, we have Joel here. Joel says, well, so he says maybe the same. And then we have another answer that says much larger. And then Katia Goya says, I
have no idea. Okay, good.
And then we have Diego Hurtada says is like 5% of the number of stars. And then we have one more answer that says about 10 to the 20th. So
okay, lots of different answers. Good.
Are we close, Vinny?
Okay, so let's see. I'll review that in a moment. Again, having questions and trying to estimate, I think that's the first step in trying to increase your understanding about something. So this is the number I have. So here you have the number of emails, right? This is the number of stars in the observable universe. So that's 10 to the 22. And I looked online, so that's 70 sextillion stars. Hopefully that's grammatically correct. And this is roughly 10,000 stars for each grain of sand on the entire planet Earth, right? So hopefully that number surprised you as much as it surprises me every time I look at it. And the reason I did this here is that the premise of my entire presentation is that if we believe that the number of stars in the universe is this big, right? What I'm trying to convince you of is that I can tell you a convincing story about the age of the entire universe and the chemistry of the entire universe just by looking at 2 stars, right? So then you may think that if this is true or false, but well, just a hint, if that was false, I wouldn't have a job today, right? I wouldn't be working here. And the answer for that is, even though it sounds really amazing, the answer is yes. So just by looking at 2 stars here close to us in our own Milky Way galaxy, we can tell a story about almost the entire universe just by looking at those 2 stars. And that's what hopefully by the end of the presentation, you will be convinced of. And 2 of our friends here, those 2 stars, they are here. Here on the left is BD plus 44493. So that's the one, the bright one here at the center. And this one here, my premise is that that star carries genetic material in terms of chemistry of the first stars to be born in the universe. So if I can correlate those 2 stars, that star with the first generation of stars, we can tell a story about the chemistry. And the one on the right side, that's RAVE J2038-0023. And that particular star here, my assumption is that if we analyze that star really well, we can place limits on the age of the entire universe just by looking at 1 star. So before we dive into the details about each of those 2 stars, let's talk about the contents of the universe as a whole, just so we can also, put things in context. So the universe today, as astrophysicists and cosmologists believe, it's made up mostly, so 71% of the entire contents of the universe are made of these things called dark energy. I won't go into detail. This is not my field of study, but we believe that dark energy is the responsible for the acceleration of this expansion of the universe. So that's dark energy. So that's 71% of the entire universe is made of this thing called dark energy. Another 24% we believe is dark matter, which is something different than dark energy, but still a little bit mysterious to astronomers. Many people studying that as well. So just by looking at these 2, 95% of the contents of the universe, we have not a lot of idea, great idea of what they are. 4% is just hydrogen and helium, just flying around space, just in gas clouds in general. 0.5% of everything that is in the universe is locked inside stars. And the tiny fraction of what's left, these are heavy elements and neutrinos, which are also really energetic particles. We won't go into details. But here, heavy elements, this is everything most of the things we have here on Earth, carbon, nitrogen, oxygen, iron, silicon, all of the elements we know, they are just this really tiny fraction. So that's the universe. So if we go a step closer and look at the sun, most of the sun, you see 71% of the entire sun is made of hydrogen, 27% helium, so 98.1% is just hydrogen and helium. And all the other elements that are really important to us to sustain life, for example, are really tiny fractions of this, of what's there in the sun. So that makes us even more special because the stuff we are made of is just a tiny, tiny fraction of something like the sun, which is really massive compared to, well, the Earth and us. So this is the sun. So if we look at the Earth, just the crust, right? Most of the crust of our planet, 47% oxygen, 28% silicon, and all other elements that you all know and love, they make smaller and smaller fractions of the crust of the Earth, right? And again, oxygen and silicon dominate, and then the other elements are just tiny, tiny fractions. And the last chart I'll show about this is our average human today. This is us, right? So we are made mostly of water. So if you look at here, hydrogen and oxygen, 75% or 3/4 of our entire body is just water. We do have 18% of carbon, 3% of nitrogen, and a lot of other stuff. And the other stuff I'm talking about, you have phosphorus, sulfur, and all the other chemicals, they make up a really tiny fraction of our bodies. And even though they're super important. So what happens is you may ask yourself, so how do these elements form and how they end up, well, in my body, in the Earth's crust, in the sun, and is spread around the universe. So one theory that astronomers believe is true is the theory of the Big Bang. And what this is telling us is that the universe started just with hydrogen and helium. So at the beginning, we just had two elements, hydrogen and helium. We did have traces of lithium, but we won't go into details. So hydrogen and helium. So how do we go from having only those two elements all the way to having the entire periodic table of elements, right? All the elements here, you know and love from your high school chemistry classes. So how do all of these elements are formed? There are some hints from the slides. So you have Big Bang nucleosynthesis, you have dying low mass stars, exploding massive stars, merging neutron stars. And the common theme from all of us is that these are all stars, right? So most of the elements, if not almost all of these elements, they are formed one way or another from stars. They could be stars burning fuel inside their own cores, or they can be formed by explosive nucleosynthesis, like exploding massive stars, white dwarfs, and merging neutron stars. All right, so these elements, many of them are just formed inside stars. So here you see just a picture of a star similar to the sun, let's say that, and here is how hydrogen, it's being fused into helium, and helium can be fused in forming carbon and oxygen. So our sun is capable of forming helium and carbon, oxygen, and then it won't be able to do anything else just because it's a small star in general. But if you have really massive and large stars, those stars can form many other elements all the way to iron. And then once they reach iron, something happens with the star, and then the star needs to explode in order to form all the heavier elements that we saw on the periodic table. And we know this for over maybe 60, 70 years now in terms of the theory of stellar evolution. So we know where all of these elements are coming from. So if we look at a picture like this, with stars here of different masses, see sun-like star, a blue supergiant, so stars being low mass like the sun here, all the way to really high masses, they all evolve in different time scales and they all form different elements. So the combination of all of those elements, when some of those stars, they explode, some of those become those pretty planetary nebula and they just, those elements just keep flying in space, so to form new generations of stars. So all of those stars, one way or the other, they contribute to the chemical makeup of the universe. So one of our objectives doing stellar archaeology is try to discover how were the first stars formed in the universe. Because if you remember what I just said, we did have only hydrogen and helium at the beginning of the universe, right? So how can you form stars just out of hydrogen and helium and then explode those stars or let those stars evolve, and then find those elements, for example, carbon, nitrogen, and oxygen today, just so that we observe them in a place like the sun, right? So then we just want to try to tell this story about those different stellar generations. So if I could find, for example, here, a second generation star enriched with a lot of carbon, nitrogen, and oxygen, for example, I could in principle say that this star here is just the offspring of this first generation of stars. And why those first generation of stars are important, because many astronomers and cosmologists, they want to know what are the masses of those first stars and just plug those numbers into models of the evolution of the universe in general and galaxies in general, right? So these numbers are fairly important. So what do we do with all of that is, well, we get the chemistry of the stars and then we try to figure out where they came from. So the step now that we need to take is how do we determine the chemical composition of a given star? Let's see if I can move this now. Okay. So how do we determine the chemical composition of a star? Just by looking at it, right? Because we are all bound to our planet. So everything we can observe, we're just observing the light coming from those objects. So there's a hint here of how we can observe and determine chemical composition is by looking at rainbows, right? If you don't remember this from your high school physics classes, that's fine. Let's just do a quick review what a rainbow really is. So what a rainbow is just this white light coming from the sun, in our case. The light will be diffracted and reflected within water droplets in the atmosphere. And then the different colors of light, the different wavelengths of light, they will be dispersed differently. And then you will see this pretty nice rainbow being formed, right? So this is the principle of how we get the chemical composition of stars. So we transform this white light here coming from the sun in all of those different colors. So, and how do we get the chemical composition from this? Is just looking in more detail. So this here that you see is just a real rainbow of the sun, which is super impressive to me because you see all the colors that you usually see, but you also see here, you notice all of those dark patches and dark, discontinuities. What these are the chemical fingerprints of the elements, right? So each element on the periodic table has a very specific fingerprint. And when I have the sunlight coming into a dispersing element, can be a water droplet or can be a prism, I can see all of those lines here. And if I can measure the exact position of them and the strength of those lines, I can tell which elements are in the surface of the sun and how much. So that's the basics of determining the chemical composition of stars. So we know from atomic physics, from hundreds of years of studies in atomic physics, that each element in the periodic table has its own fingerprint. So this is just a different version of the periodic table that we all know and love. And this is showing that every box here is a different chemical element. And you see that all the lines, they are just different positions of lines. So these are just the chemical imprints, the fingerprints of each element. So if I observe a star in the sky that I don't know anything about, and if I can identify those lines, just like we do here for the sun, in principle, I can tell the chemical composition of that particular star. And this is what we are going to do right now, right? So let's try to determine the chemical composition of one star. Oh, I see Jamika here, yeah?
Yes, Vinny, thank you. I just have a question from Diego. Diego asks, why are there, so you're showing us the chemical elements, the chemical fingerprints of the elements in the periodic table. And so Diego asks, why are there some that actually have a gradient with their colors and others that are just a plain line?
Okay, so talking about this picture here, what we are doing is just going from blue to red just to follow the colors of the rainbow, right? But then what's really important here when we try to identify different chemical elements, it's actually the position of those lines. I think the colors here are just to make it so that you understand that the blue lines are on the ultraviolet regime, wavelength regime, and the red ones are in the infrared, going towards the infrared. But what's important here is the actual position. And the reason you see a gradient here is just because we are following the colors of the rainbow, right? Which are just the real colors of the light being dispersed by a prism or the water droplets. So hopefully that answered the question. So now that we know more or less how to do this, let's try to observe a star. So the first thing we need to get a stellar spectrum is a big telescope. So Gemini has two big telescopes. This one is the Gemini South in Cerro Pachon. And well, it's a big telescope and you can see there's clouds here and you may think, well, so how can you observe with clouds? So one of the reason I put this picture here, it's not only it's pretty, but the Gemini telescopes, they're so powerful that depending on what you want to observe, bright stars in my case, you could even observe those stars through really thick clouds. Right? So you can actually do that. So this is just a picture to let you know that this is possible. So these telescopes are just massive and they're super powerful. Okay, so let's try a clearer night. So this is the Gemini North in the island, in the big island of Hawaii. And just so you know, you have an idea of the size, this is a big truck just parked here in front. So here you can see the dome and here you can see the actual telescope. So what we are going to do now is the following. So we find an interesting star in the sky. Let's try BD plus 44 first. So we find the star. We point the big telescope towards that star, right? You see here the big mirror. So this is 8 meters across. I think this is 24 feet. I always don't get the conversion between feet and meters, but this is 8 meters across, right? So what happens is you point the telescope to your star, then the telescope will collect all that light. The light will be collected in this mirror. It will go to a secondary mirror. It will go inside the tube here to the back of the telescope, and then the light will be directed to one of those boxes, which are dedicated instruments that serve a specific scientific purpose, right? So in our case, we are using a spectrograph because we want to disperse the light and get the actual rainbow. So once you get the light in one of those boxes, this is how one of those boxes look like. This instrument is not on the Gemini telescopes. This is one of an instrument for a space telescope, but I just wanted to show you just the amount of engineering in optics, that these are just really complicated instruments built by physicists, engineers, astronomers, all combined. And within those instruments, you have lots of optical elements that will get your light coming from the star. That light that comes as white light, let's say that, it will be dispersed in a prism-like device, and then you will have your rainbow here, and that rainbow will be recorded in a camera, just an upscale camera, a version of the camera that you have on your phone. And then you will have your rainbows here. So the rainbows are usually not colorful. What astronomers like myself work with, we usually work with the grayscale versions, because the colors don't mean much to us in that sense. We just want to find the position of each and every one of those dark patches here and measure the strength of all of those. So then we measure this, right? So we have those two things in here. So now what we do is we transform the rainbow into a thing that we call flux as a function of the wavelength. So you can think of this as, if you look at the bottom, at the upper panel here, we transform each and every one of the dark patches in an absorption feature here. See, that big strong one here relates to this one, then this one here, this one, and so on and so forth, right? And that's easier for astronomers like myself, because then I can measure the exact position here on this axis that we call wavelength. So we measure this wavelength, and if we can measure the exact position of this line, and we compare with theoretical tables coming from atomic physics, for example, I can tell which element is in the atmosphere of the star. So these are 4 different stars, and just by looking at them, you can see that they all look really different, because stars are not all the same. They have different temperatures, different gravities, and different chemical compositions. And what some of those lines here are telling us is just giving us the chemical composition of those 4 stars in here. And here are just a couple of examples, just so you understand how those lines translate into chemistry. I know, because I've seen, well, thousands and thousands of those over the past 10, 20 years, I know that those 2 lines are hydrogen. We have calcium lines here. We have a big carbon feature here. If we go to the top, you see the same calcium lines here and there. You see the same carbon feature, for example, here and here. And you see magnesium and other elements. So just by looking at those stars, I can tell which elements they have already. It's not a very precise measurement, of course. I cannot quantify that just by looking at them. But I can, for example, look at these 2 and tell that, well, if this line here is actually stronger, this one has more carbon than this one, roughly. Oh, hi, Jamika.
Hi, Vinny. Super engaging presentation. I am really enjoying it, as are our YouTube audience members.
Hopefully, yeah.
Yes, absolutely, they are. You have lots of support out there. So many people joining us in the chat from Brazil. I'll point out just a few. Of course, we have, starting out, our first guest here was Juliana Placco, followed by Inez Placco, and then they're all saying hello and greetings. Diego, of course, Joel, Marcelo, Sylvia, quite a few in the chat today. Katia, all are really enjoying your presentation.
Mostly family, so that doesn't count much. And there's extended family, so they're required to join and enjoy. So thank you.
Well, we are glad that they are here with us today. And also we have the Maple Family Canada from Toronto who are with us. And Joel Riverboat just said that he is joining us from lovely, sunny Arizona.
Very good. So am I.
That's right. Okay, so as we're looking at your slide here, the current one with telling us what the rainbow is here, flux versus wavelength. And I love that you have highlighted here the chemical elements and describing how we know what we're actually looking at here. But as we're looking at these lines, could you explain the difference between an emission line and an absorption line?
Yes, I can explain a little bit. So the difference between, well, these are all absorption features. And the reason they're called absorption features, you can think of, for example, the sun emitting light from the center, right? And then you have all of those chemical elements in the atmosphere of the sun. And depending on the elements that are there, they have different fingerprints, as we saw, right? So if you take, for example, hydrogen has very, based on its fingerprint, it has very specific wavelengths of energy that it actually likes. So if the sun is emitting light, and if the hydrogen atoms see a wavelength of light that they actually like, they will steal that light from the sun, and they will absorb that light. And once they absorb that light, then you have a dark patch in your spectrum, because if you look in here, the reason that it's dark is because this particular wavelength of light is missing. And the reason that it's missing is because something stole it. And the reason it was stolen is because that particular atom had a fingerprint that liked that particular wavelength. So it stole that light from the surface of the sun. So all of those dips here, they are just light being stolen by very specific atoms. So these are absorption. The difference with emission is because, well, you wouldn't have a source of light at first, right? So the reason we're talking about the difference between emission and absorption is absorption, you're just absorbing light, and the emission, you would just be emitting, just like we saw on the previous slide. Let me just go back to this. If you look at this one, for example, these are just emission lines, because these elements in particular, they're just emitting those packets of light in those very specific wavelengths, right? And since they are emitting, those are, well, they're just shining in those specific colors. Hopefully that made a little bit of sense. I know that there's a lot of theory embedded in that, but that's, I think, as far as I can go for this. And if there's not enough, we can talk more about this later. Is that okay, Jamika? Does that answer?
Absolutely, Vinny. Thank you. We appreciate the explanation.
Okay, good. So then let's look at this one again. So we look at those lines and we know that the chemistry, it's just embedded in those lines. There's other effects, there's temperature, there's gravity, and there's other things happening, but chemistry here is dictating a lot of the features that you see. So by using, well, the work being done by many physicists and astrophysicists, I can actually transform the dips in here. I can apply physical, astrophysical equations, and I can transform those dips into actual numbers, which I call the chemical abundance of a given element, right? And so we can go in a little bit more detail, right? So here you see hydrogen, carbon, calcium, but we could in principle measure everything that we see on the periodic table. Here I have lutetium, hafnium, barium, lead, niobium, and gold. So these are elements that you probably heard of on the periodic table. In all of those, we can find in the surface of the sun and in the surface of other stars in the universe, right? And these here, what you see here are just different versions of the spectra that we just saw. The dots here, these are all the observations that we do. So we observe flux as a function of a wavelength here. And all the different lines are just different theoretical predictions that we try to match with the observations, just so we can declare that we do see that element in this particular star, right? So there's a lot you can do in terms of chemistry. So we look at all of those stars in lots and lots of detail. So now let's go back to our two stars and just wrap this up. So if we look at BD plus 44, I'm trying to tell you that this star is the offspring of the first stars to form in the universe. And the reason I can tell you that is that we observed this star here several times with many, many different telescopes, and we determined lots and lots of different chemical abundances for that star. So here in this picture, what I'm showing you is the element. It goes from carbon, nitrogen, oxygen, all the way to zinc. And all the red squares here, these are the actual measurements that we took based on what I just explained you. And the lines here, all the different lines, these are theoretical predictions of the chemical abundances of the first stars to be born in the universe. So we do have collaborators who, instead of observing stars, they model stars in their computers and they explode supernova in the computers. And what they give us is a table of predictions. So I get the table of predictions from my colleagues and I have my observations. So the job is, let's compare observations with predictions and see how well they match. So as you can see, some elements, they match pretty well with some of the lines. So that means there's a good agreement. Some of those, they don't match very well. So maybe that's a problem with the theory, maybe that's a problem with the observation, then we have to talk about. But if we can infer that this line here, the black line, for example, is a good explanation for all of those observed points, I can match the theory, the predictions with the observations, and I can say that, well, the star that exploded in the computer may actually have existed at the beginning of the universe, and then it gave birth to the second generation stars that I observed today, right? So just by looking at this one star, I can actually have predictions for stars that were born at the beginning of the universe 13 billion years ago. So that's our BD plus 44. So let's look at RAVE J2038 now. So that's the red star over here. And for this particular star, what we do is we have a technique called cosmochronometry. And the reason this is called cosmochronometry, that goes along with the field that I am in, it's called stellar archaeology. And we call this archaeology because we use things that we saw also in high school. For example, I'm sure that you remember half-life. If you don't, well, I won't tell on you, but yeah, half-life. You remember carbon-14 dating, right? When you have fossils, one of the ways that you have to determine how old a fossil is just by measuring the amount of carbon-14 in that particular sample. And by doing that and comparing with carbon-14 that we see today, and comparing with this half-life of the carbon-14, in principle, you can tell how old a sample is. So carbon-14 can be used to date samples of fossils up to 100,000 years, I think. However, if we want to date the entire universe and know the age of the universe, we cannot use carbon-14. We need something a little bit more robust. So we do have other elements with other half-lives. And as you can see in here, uranium and thorium, they do have half-lives that are pretty similar to the age of the universe. This age of the universe here, 13 billion years, 13.7, it's a prediction from the Planck satellite, right? Looking at cosmic microwave background radiation. So this is what we have in terms of the age of the universe, right? So if we look at, for example, thorium and uranium, if we could in principle measure the abundances of those two elements in the surface of a given star, and if we plug those numbers into equations that we know and that are calibrated by nuclear physicists based on production ratios and the way that those two elements decay radioactively, in principle, we can find an age for a star. And for this particular star, RAVE 2038, we did find uranium and thorium. And here again is just the spectrum of these star, two small sections. Again, the dots here are just the observed points. Again, flux as a function of wavelength. And here are the points. And this black line here is just my prediction of a given uranium abundance for that star. So since I can match my prediction with observations, I can say with a lot of confidence that I can see uranium in this star. And the same thing with thorium here. So if I do measure thorium and uranium in this star, I can go back to the equations, I can put the numbers in here, and I can calculate an actual age. And the age I calculate, I apologize that this graph here is a little bit confusing, but let's just look at the line here. So if I calculate here thorium and uranium abundances for this particular star, I find an average age of, maybe I don't know if my camera is just in front of the numbers. So we found an age of 12.98 billion years old for this particular star. So what does that mean? That means that if I can observe a star inside the Milky Way that is 12.98 billion years old, that means that the universe has to be at least that old to accommodate the fact that I could form a star in it with thorium and uranium, right? It's kind of a fair assumption, right? Because if I can measure that and if I can determine the age of a star, something has to happen before that star was born that actually formed that thorium and formed that uranium, so I could measure that in that star today, right? So this is how we determine the age or place a limit on the age of the entire universe just by looking at one star. And this is coming to, well, the end of my presentation, and I'll just move back to my slide here with my two favorite stars, at least for now. So just a brief overview. So what I tried to convince you, and hopefully I did convince you at least a little bit, is that just by looking at single stars in our own Milky Way galaxy, really close to us, relatively speaking, in terms of the size of the universe, we can in principle limit what happens with the entire universe in terms of age and chemistry just by looking at these two stars. And hopefully the presentation was clear enough. I think I went over time a little bit, hopefully not too much. I wanted to thank everybody for taking the time to see this presentation. For those of you who are not part of my family and don't have any other ways to communicate with me, I'm putting my email here. So if you have any questions, please feel free to reach out by email. The US NGO, which is the National Gemini Office, which I currently work, we do have a Twitter account now. So follow us on Twitter. And I do have a website that shows a little bit of my research and other things, interesting things you can look at. So thank you very much. Thank you again, Jamika, Elise, and Peter for the invitation. I'm happy to take any questions you may have.
Fantastic, Vinny. Thank you so much. So in the chat, we have some more people who have joined us. We have Michael Mosby from Memphis, Tennessee, who says that we love the presentation and love watching NOIRLab. Also, the Maple Family Canada say this topic is fascinating. Congratulations on your presentation.
Thank you.
Vinny. So, and again, Katia Goya says, excellent presentation. The images are excellent as well, as Katia
Thank
says.
you.
I have to agree. I really appreciate how clear the images are and how you connect them to what you're trying to explain to us. So great visuals.
Thank you. It was a lot of work, so appreciate it.
Absolutely. We appreciate you. So you spoke just a little bit about the U.S. National Gemini Office. Could you give us a little bit more info about that? What is it and what is your role?
Yeah, so, well, as Alisa told us at the beginning, so the Gemini Observatory is a collaboration between different countries, right, different partners, and each partner has its own National Gemini Office. And in the case of the US, we have two people, myself and Letizia Stangelini from NOIRLab. So our job is to enable and help US users of Gemini to make the best use of the observing resources provided by Gemini, right? We can help with people designing observations and looking at their science and saying, hey, this science would be good for this instrument and this instrument or something like that. We can help with data reduction. Once your data comes from the telescope and you have your proposal accepted, we help with data reduction and making sure that the data is optimal so the astronomers can do their science. So that's one aspect of what we do. We can also serve as a bridge between the observatory and the US community in our case, and the other Gemini offices do that for their own communities in Brazil, Argentina, Chile, Canada, South Korea, and also in Hawaii. So we can serve as this bridge between the observatory, the scientists as the observatory, and the actual users. And another aspect that I see is that we are also with a task to protect Gemini, right? Protect this very pristine resource that astronomers have. Gemini is paid with taxpayers' money, right? So this comes from the NSF, it comes from everybody's taxes. So we need to make sure that the science being done with Gemini, it's communicated throughout the community and people, the general public and astronomers know what great science is being conducted with all of those resources, right? So this is, I think, is to me is a really rewarding job. This is to me the best job I can have, and it's just making sure that everybody understands how good and how important those resources are, not only from basic research, but also from an outreach perspective.
Well, I think you're doing an amazing job being here and sharing your science with all of our audience on YouTube. Thank you to everyone who's joined us. We do have 14 minutes left for the show. So if you have any questions at all, whether it's about this presentation or any astronomy questions in general, our guest, Vinny, was a professor for a while, so I'm sure he can answer any and all of your questions. There are no bad questions out there. But speaking of, to segue off of the fact that, yes, observatories are services to our national audiences, right? Can you explain a little bit more about the actual product that comes from the telescope itself? So you showed us a lot of pictures today, and I'm just wondering if for our audience, you can explain when you first take that observation with the telescope, do you actually get these star pictures that we're seeing right now, or is it something more of lines or a graph or a beautiful rainbow?
Mm-hmm. So that depends, right? Depends on the telescope, depends on the instrument. So in my particular case, well, so you could get images like this, depending on the type of science that you're doing. If you're doing photometry, for example, then you would have an image like that. In my case, since I'm doing most of my personal research is spectroscopy, let's see, just usually what I get from the observatory is something like this, right? So this is what we call a raw spectrum. And then with this, we would have lots and lots of different calibration type images, and we have a raw spectrum. And then we would run reduction packages. And these are some of the things that the US NGO works is trying to provide, and Gemini as well, of course, just provide reduction packages that would help the users go from this over here all the way to this. So in order for me to do my science, I need something like this, right? Something like these guys or something like this. So then there's a pretty long way between the observation just finished at the telescope and getting this. So one of our jobs at the US NGO as well is try to minimize that time frame. Because if I can get something observed tonight and tomorrow I have something like this, I can start doing science right away. So then the turnaround, then I can publish a paper sooner, and then that increases the visibility and everything else percolates from that, right? So in my case, what I usually get is just what we call the raw spectrum. They will look something like this.
Great answer. Thank you so much. But speaking of that turnaround time, what is it right now without all of those systems quite in place just yet?
Can you say that again, Elisa?
So astronomers are able to receive this raw spectra right away after the observations.
Mm-hmm.
And if they wanted to process that data, so for your own science, how long has it typically taken you to go from raw data to finished paper, and what are some of those steps along the way?
Okay, and that also depends a little bit on the area that you are, the size of your collaboration, the number of co-authors you have on a given paper. But I have maybe two extreme examples. We did have maybe 4 or 5 years ago, one really interesting star that we observed. So we got this spectrum here on a given night. So we got this at night on a given night, and the following, well, at the telescope, after the star was observed, we reduced the data and we saw that the star was really interesting. We analyzed that, wrote a paper, and 1 week later, the paper was submitted. And this is, again, it was super fast because the star was super interesting, and it was just one star. However, if you're doing statistics, for example, and you're observing 100 stars, it may take up to a year for you to get all of your data and then write the paper. And then depending on, again, how many people you have within your collaboration that have to do different steps of the analysis. But it can, I've seen people do that in matter of days and weeks, depending on how interesting the star really is in terms of a timely discovery. But some other work, depending on the field, it can take a few years, so you can collect a meaningful sample and then you can analyze that sample. And yeah, so it varies a lot. In my experience, maybe 1 year from inception of a given project all the way to submitting a paper. That time scale. You know.
All right, thank you for that answer. Yes, I think a lot of our audience is very familiar with the amazing discoveries that we come out with here at NOIRLab, but the behind the scenes process is sometimes a bit of a mystery, and I think it's really great to sort of showcase the great things that we're trying to do to get that data and get those discoveries more streamlined.
Yeah, and well, if I can say, I think one really important thing is that even though the final product is an online article, it's not a paper anymore, right? It's just 10, 20 pages of text with figures. All of those results, they're just the work of so many people, right? There's so many people behind the scenes supporting, making sure that everything is working every day, making sure, the amount of people working at an observatory. I think NOIRLab has 1,500 employees. Is that right? That's the number I have in my head, something like that, right?
I think we had an all-staff meeting this morning, and if I'm remembering correctly, they said 500 people are employed by
okay. I had 15 in my head, but even so 500 people have to work really hard to do their own thing correctly. So everyone's job is important in that sense. So there's contribution from so many people that not necessarily have their names on the paper, right? And that's why we have many acknowledgements, and there's a lot of people, not only in science, but people at home supporting the scientists so they can do their job properly. And yeah, so then, yeah, it's never an individual accomplishment, right? It's a teamwork, and whatever your team might be, right?
Yes, that's a great reminder for pointing out just how collaborative astronomy is, from the moment of observation to the paper on a discovery. Yes, it takes a whole observatory, which is not just astronomers, right? It's many, many different careers. But I think something else to say about how collaborative astronomy is as well is the fact that a lot of discoveries take multiple telescopes as well. So for you yourself, do you use a variety of telescopes? And could you tell us about what some of those are?
Oh yeah, absolutely. So we use, so it's a collaborative endeavor, right? So I do have lots of collaborators here in the US, a lot of people in Brazil, people in Europe, people in Asia. And depending on which country you are, you have access to different observing resources, right? So that's the good thing about having friends, and while keeping good relationships with those friends, keeping fair relationships with them means that you can leverage some of their observing resources. So I've observed with many different telescopes in Chile, the SOAR telescope, Gemini, telescopes in Tololo, like the Blanco 4-meter. We do have things here in the US at the McDonald Observatory in Texas, the Magellan telescope in Chile, Gemini, Subaru telescope, CFHT, and Hubble Space Telescope in space as well, right? So I think having lots of collaborators and being good standings with all of them, it means that you can enjoy all of those resources. And you're absolutely right. Sometimes those telescopes, depending on the type of science you do, if it's something that is really time sensitive, having access to different resources at different times, that's crucial for, well, specific types of science. Not in my specific case, but yes. You have to have lots and lots of friends. Yeah.
Okay, so we have another question from the chat, Vinny. And well, first we have a comment and then I'll go to the question. This comment is from your ex-advisor. Well, your ex-advisor is here in the chat saying hello to Sylvia Cristina Fernandez Rossi. So happy to have you with us today. Okay, so question here from I don't want to mispronounce your name, Mr. Limburg here. And the question is, asked a clarifying question too. So he asked, can you tell us some of your recent projects? And then he goes on to say, like, what specific questions he thinks are important to astrophysics right now. So we appreciate your insights, Vinny.
Okay, well, first from Sylvia's comment. So Sylvia was my advisor and supervisor for maybe more years than I want to admit. I think we we still work together today, but I met her when I was an undergraduate back in Brazil. So we have been working for many, many years, and she has been supported through all my entire career. So thank you for being there as well. And the question, I think, is from Guilherme, who is a graduate student now in Brazil as well. So shout out to him in there. So things that I've been doing now, I keep observing those stars. I think now I'm interested in finding ways of identifying interesting targets from imaging. So looking at things like, well, my final slide, let's see if I can move there. So looking at images like this, but not with broadband filters, just looking at narrowband filters, and I won't go into detail because I think most people wouldn't care too much for the details, is just looking at those images, see if we can select interesting candidates and then do the spectroscopic follow-up. Because as you can imagine, to get one spectrum in really high detail, to get, for example, the uranium abundances, it's super expensive. That costs one entire night of a big telescope like Gemini, for example. And this is super expensive in terms of time and in terms of competition. So we need to be really good at selecting interesting targets, because I cannot just go to Gemini and say, hey, give me one night because I want to try something, right? You need to be pretty sure that you have an interesting star just so you can do the follow-up. So now we are trying to identify interesting targets, so we have more, for example, uranium and thorium measurements, and we can tell constraint theories for our process nucleosynthesis, for example, and try to connect those with recent kilonova observations coming from those gravitational wave signals from neutron star mergers. So then it connects all together. And so lots and lots of follow-up spectroscopy. So that was the first question, and I forgot what the second one was.
Well, he was really just, I believe, asking for more, just a little bit more clarification on exactly what he was asking about about your projects. But I think you give a very thorough answer, Vinny. It's very good. Yeah,
good,
absolutely.
Good. Mm-hmm.
And so I'll say, with just 2 minutes left, thank you to everyone. A big mahalo nui loa to everyone in our YouTube audience. Thank you so much for joining us. The recording of today's show should be available within the next 24 hours. And if you are unable to ask your question, or if you didn't have a question or a comment yet, but you do after the show, please feel free to leave your questions and comments in the comment section of the video, and we'll be sure that Vinny gets them. Thank you so much, and back to Vinny and Alyssa.
From my end, I think, well, you have my email here. Please feel free to reach out if you have any questions, if you want a copy of the slides. All of this, again, it's free knowledge, so it's there for everybody. And again, I want to thank you, everybody, the organizers and everybody who's watching and everybody who's supported me throughout the year so I could get here. So you know who you are, but I really appreciate it. Thank you.
And thank you for being here with us today, Vinny, and to Jamika for moderating. Vinny, how about you give one last little piece of advice for any future students out there who want to be an astronomer?
If you want to be an astronomer, well, you need a really good support system, right? People who believe in you and people who are willing to make sacrifices for you. I think that's really important. And you need to be, well, not afraid of challenges, right? It's 95% effort and 5% everything else, right? Just really fight for it. You have to work really, really hard. And if you like astronomy, if that's your passion, or if your passion is paleontology, go for it. I think that's one piece of advice. And the last piece of advice is that you have to be prepared to identify opportunities once they present themselves to you, right? It's not only, you have to be prepared, right? Fortune favors the prepared mind, right? So you have to be prepared, with the right skill set, with the right collaborations, and with the right support system to be able to identify opportunities and just grab them and just go forward, right?
All right, thank you so much. And on that note, take care, everyone. Happy holidays, and we'll see you next week for another Live from NOIRLab.
Thank you. Bye-bye.